Hello everyone, welcome to the next session on forces on bend. Before seeing the equations which we use for calculating the forces on a bent pipe, we will first see what is the momentum equation. The momentum equation says that the net force acting on a fluid mass is equal to the change in momentum of the flow per unit time in that direction. It is nothing but the Newton's second law, which means that the net force acting on the body is equal to mass into acceleration of the body in the direction of the force. For acceleration, the formula is dv upon dt, which is the rate of change of velocity. When I substitute the acceleration value over here, I get F is equal to m into dv by dt. M is a constant term as the mass of the body cannot change, so I can take this term inside the derivative. So here I write d mv upon dt. When I write d by dt, this is ordinary differential equation and these two can be separately written. So I transfer this term over here and I get f into dt is equal to dmv. Now d into mv is nothing but the change of momentum. M into v is change of momentum. So the rate of change of momentum is equal to the net force acting on the body. This is called as the momentum principle, and when I multiply this dt term over here, what I get on the left hand side is F into dt, the rate of change of force, which is nothing but impulse, and this is the change of momentum. So this equation is called as impulse momentum equation. Now let's start with forces exerted by a flowing fluid on a pipe bend. Now I have a pipe over here which is bent at an angle theta. Fluid is flowing in this direction, this way and then out. Now this pipe which you see can be either horizontal if I say that it is lying on the floor, or it can be vertical wherein I can say this much portion is on the horizontal surface and this is on a vertical surface. For complete horizontal plane, the example will be pipes which are laid on the ground for supply of water to the buildings. And when I say vertical, I mean when you vertically lift water from the ground to the top surface for again supplying water in the building. Now here we are going to use the impulse momentum principle. This is my pipe. This is the flow of water. Say it is entering with velocity v1. The pressure is p1. I consider a section here and a section here. At this section, the force acting will be P1 into A1. This is the pressure force exerted. On this section 2, you can see there will be a pressure force exerted which is P2 A2, and the water is leaving the system at velocity V2. Now this portion 1 to 2 is nothing but my control volume, which we have already discussed before. Here I have marked Fx, which is the force exerted by the water on this bend, and Fy is the force exerted by the flowing fluid, which is water over here again on the bend. So you will have two directional force Fx and Fy acting on this bend. So this is the direction marked here, and here what you can see is the resultant. If you observe carefully, this direction V2 is at an angle of theta with respect to Fx. So this resultant can be solved in two components, V2 cos theta and V2 sin theta, which is shown over here. Similarly, this P2A2, which is again at an angle of theta with respect to the ground, can be resolved into two components, the cos and the sin component. Now, the component of force exerted by the bend on the fluid will obviously be minus Fx, because Fx is the force exerted by the water on the bend. And in the y direction, the force exerted by the bend on the fluid will be minus Fy. Now let's talk about the pressure force on the section 1, which will be P1A1, and pressure force on the section 2 will be P2A2. Now what I am going to do is I am going to use the principle which is of momentum. The net force acting on the fluid in the x direction is equal to the rate of change of momentum in the x direction. Now if you look carefully, the forces which are acting in the x direction are P1A1, which is acting towards the right. So let's assume the sign convention as positive moving towards the right. P2A2 cos theta is also a pressure force exerted in the x direction, but the direction is opposite to that of P1A1, so I'll take this as negative. So the two forces which are marked over here, so you can see the force over here P1A1 minus P2A2 cos theta. Also there will be a force component which we have just discussed, that is the force exerted by the bend on the fluid. So that is going to be minus Fx is equal to, on the right hand side, it is rate of change of momentum in the x direction. Now rate of change of momentum can be written as mass per second which is flowing into change of velocity. Mass per second is rho into q, and change of velocity is final velocity minus initial velocity. Now if you look carefully, it is again going to be rho q into the velocity component in the x direction. Final velocity is v2 sine theta minus the initial velocity is v1. So I have written v2 cos theta minus v1. Hence Fx can be resolved as rho q v1 minus v2 cos theta plus p1a1 minus p2a2 cos theta. You need not by heart this formula. This formula can be derived every time for a numerical that you solve. This is just the explanation given. Now similarly, when I solve for the momentum equation in y direction, if you look here, p1a1 term becomes 0, p2a2 term is present, p2a2 sine theta in downward direction, so I have written minus p2a2 sine theta, minus Fy term will be there, which is the force exerted by the bend on the liquid, is equal to rho q into the final velocity is v2 sine theta in the upward direction. I am taking the sign convention as positive, so it is v2 sine theta minus initial velocity v1 does not have any component in y direction, hence it is 0. Now when I solve this, I will get Fy is equal to minus rho q v2 sine theta minus p2a2 sine theta. This is just a formula, you need not remember it, you need to solve it every time for a numerical given. Now resultant force Fr is equal to root of Fx square plus Fy square. This is the formula for calculating resultant, and the angle made by the resultant with the horizontal axis is given by tan of alpha is equal to Fy upon Fx. We need to calculate this angle alpha. Now let's take up some numericals on forces on bend. The first one, a 45-degree reducing bend is connected in a pipeline. The diameters at the inlet and outlet of the bend being 600 mm and 300 mm respectively. So the angle of bend theta is given as 45 degree. The diameter at the inlet D1 is 600 mm, which is 0.6 meter, and the area A1 can be calculated using the formula pi by 4 D1 square. Diameter at the outlet D2 is given as 300 mm, which is 0.3 meter, and A2 can be calculated as pi by 4 D2 square. Find the force exerted by the water on the bend if the intensity of pressure at inlet to bend is 8.829 Newton per centimeter square and rate of flow of water is 600 liters per second. The pressure at inlet P1 is given as 8.829 Newton per centimeter square, which I have converted here into Newton per meter square, and the rate of flow Q is given as 600 liters per second, which is 0.3 meter cube per second. Now we are supposed to find Fx, Fy, Fr and the angle alpha. The first thing that I do is draw the diagram. I have to first draw the center line of the pipe, and then I draw this angle theta, which is 45 degree. Then I will start drawing the pipe according to the diameter which is given to me. At section 1 diameter is 600, at section 2 diameter is 300, which means my pipe should have a varying cross section. So I have drawn a larger diameter here and a smaller diameter here. At the section 1 the velocity is v1, which is of the water entering, and at section 2 the velocity is v2. The pressure force exerted on the first section will be P1A1, and the pressure force exerted on the section 2 will be P2 into A2. This direction will have a force which is Fx, which will be force exerted by the water on the bend, and in the y direction I am going to show the force Fy, which is the force exerted by the water on the bend. Now let's start solving. From the given data I know that area is given to me and discharge is given to me. So I can use the formula Q is equal to A1 V1, from where I can get the value of V1 from here as 2.122 meters per second. Also I know Q is equal to A2 V2, so V2 can be found as 8.488 meters per second. Now I know the pressure P1, which is the pressure at the inlet. I need to know the pressure at the outlet. So I am going to apply Bernoulli's equation between the section 1 and 2. Bernoulli's equation is P1 upon rho g plus V1 square upon 2g plus Z1 is equal to P2 upon rho g plus V2 square upon 2g plus Z2. Now since the pipe is horizontal, my Z1 and Z2 term will get cancelled out. Now how did I assume that it is horizontal? Because it is not mentioned in the question that it is a vertical pipe. If it is a vertical pipe, it will be mentioned in the question. Until and unless it is mentioned, I can assume that the pipe is horizontal. Now, what remains is P1 upon rho g plus V1 square upon 2g is equal to P2 upon rho g plus V2 square upon 2g. I know the value of P1, rho g, V1, V2. When I substitute all these values, I'll get the value of P2 as 5.45 into 10 raised to 4 Newton per meter square. Now, I have to calculate the forces on the bend in x and y direction. So, I am going to again use the same equations as I have used during the study of theory. Now, when I look at this figure, I will know the equation has to be written as P1A1, which is in the positive x direction. So, I take P1A1 as positive. Then I have P2A2, which I have resolved over here. P2A2, which you can see. P2A2 was in the downward direction. I have resolved as a cos and a sine component, and V2 was in the outward direction, V2. So here I have V2 cos theta and I have V2 sine theta. Theta is 45 degree. So this will be minus P2A2 cos 45, and it is always minus Fx is equal to rho Q. Final velocity will be V2 cos theta in the positive direction minus initial velocity V1, which is again in the positive direction, so I take it as V1. Had this been in the other direction, I would have taken another minus sign over here. This minus sign comes from the formula final velocity minus initial velocity. So it is just the final velocity written here and the initial velocity written here. When you substitute all the values that is known to you, you will get the value of Fx as 19.91 kilonewton. Now let's solve for y direction. For y direction, my P1A1 term will become 0 because P1A1 has no component in y direction. P2A2 has a component in y direction which is in the downward direction. So I will write minus P2A2 sine 45. You will always have to add a minus sign for the Fy because it is the force exerted by the bend on water is equal to rho Q. Final velocity is V2 sine 45 minus 0. V2 sine 45 is positive because it is in the upward direction, and V1 is 0 because it has no component in y direction. From here, if you substitute the other values, you will get the value of Fy as minus 6.322 kilonewton. Resultant force Fr is calculated using the formula root of Fx square plus Fy square. If you substitute the value of Fx and Fy, you will get Fr as 20.890 kilonewton. And last but not the least, you have to calculate the value of alpha. So use the formula tan of alpha is equal to Fy upon Fx. If you substitute, you will get the value of alpha as 17 degree 36 second. This is the angle made by the resultant force with the horizontal axis. Let's take up another numerical. 250 liters of water is flowing in a pipe having a diameter of 300 mm. So the rate of flow Q is given as 250 liters per second, which is 0.25 meter cube per second, having a diameter of 300 mm. Now there is only one diameter mentioned in the question, so I am writing diameter of the pipe at inlet and outlet is D1 equal to D2 equal to 300 mm, which is 0.3 meter. So the area A1 and A2 will be same, which is pi by 4 either D1 square or pi by 4 D2 square you can use. The answer will be 0.07068 meter square. If the pipe is bent by 135 degree, that is change from initial to final direction is 135 degree. Now angle of bend is given as 135. We need to see the figure first because this is very important. What I have done is I have first drawn this horizontal axis, then I have marked the angle at which the pipe is bent. Now it is not mentioned whether the pipe is bending anti-clockwise or the pipe is bending clockwise with respect to horizontal axis. It is my pure assumption that I have marked as anti-clockwise. You can also solve the problem by marking the axis something like this, and you can mark your angle in the downward direction. In that case, you will have some other values as the answer. Now here this is 135 degree, so this angle is 45 degree. Now I am marking V1 as the inlet velocity, V2 as the outlet velocity. I have marked to section 1 and 2. On the section 1, the pressure force, the total pressure force is P1A1. At section 2, the total pressure force exerted will be P2A2. Now these P2A2 and V2 are at an angle of 45 degree with respect to horizontal. So this is the resultant value and I need to solve them in their cos and sine components. So with 45 degree, this P2A2 becomes P2A2 cos 45 and the sine component is P2A2 sine 45. Similarly, V2 has been resolved over here. Now we need to only take care of these direction because they are ultimately going to give you the direction of the cos and sine components. This is very important for solving the problem. If these directions are assumed wrong, in that case the entire question will give you wrong answer. Let's read further. The pressure of water flowing is 39.24 Newton per centimeter square. We have to find the magnitude and direction of the resultant force on the bend. So the pressure P1 and P2 is same. It is 39.24 Newton per centimeter square, which is again converted into Newton per meter square. We have to find Fx, Fy, Fr and alpha. We'll start with Q is equal to A1 V1 is equal to A2 V2. I know the value of Q, I know the value of A1, so I can find the value of V1. Now whatever is the value of V1 will be the value of V2 because Q and A both values are same. Now we need to calculate the forces on the bend in X and Y direction. For that we have to refer the figure. For that we need the first force is P1 A1, which is positive because it is in the positive X direction. Next I have to see the P2A2 component. Here if you observe, P2A2 cos 45 is again showing towards the right direction. So I have written plus P2A2 cos 45. This term is always minus Fx is equal to rho Q. Final velocity minus initial velocity. Now here the final velocity V2 cos 45 is moving towards the left. Hence I attach a negative sign. This sign comes from final minus initial. So I have not taken V1 as negative, it is just the sign of the formula. And V1 is positive because it is going towards the right direction. Now if you solve this, you get the answer of Fx as 48.85 kilonewton. Next we will go for Y direction. For Y direction, P1A1 component is 0 as it is only in the X direction. P2A2, there is a component in Y direction which is downward. Hence I will take minus P2A2 sine 45. It's always minus Fy is equal to rho Q into final velocity over here is moving upwards, so it will be V2 sine 45 minus initial velocity is 0 as it has no component in Y direction. When you solve, now there is a negative sign which I get with Fy. I get minus 20.236 kilonewton. This negative sign indicates that Fy acts in the downward direction. I have to calculate the resultant force which is given by the formula root of Fx square plus Fy square. When I substitute the value of Fx and Fy, I get this answer as 52.88 kilonewton. If you look carefully, Fx is positive, so it is moving towards the right. Fy is negative, so I have shown in the downward direction without the negative sign. It is just showing the direction. And this is Fr which I have marked at an angle alpha, which can be calculated using formula tan inverse of Fy upon Fx. If I substitute the value of Fx and Fy, I get alpha is 22 degree 30 minutes. Let's take another numerical. In a 45 degree bend, a rectangular air duct of 1 meter square cross-sectional area is gradually reduced to 0.5 meter square area. So the theta value is given as 45 degree, which is the angle of bend. Area of section 1 is given as 1 meter square. Area of section 2 is given as 0.5 meter square. Find the magnitude and direction of the force required to hold the duct in position if the velocity of flow at the 1 meter square section is 10 meters per second and the pressure is 2.943 Newton per centimeter square. So the velocity at section 1 V1 is given as 10 meters per second. Pressure at section 1 P1 is given as 2.943 Newton per centimeter square. I have converted Newton per centimeter square into Newton per meter square. Take the density of air as 1.16 kg per meter cube. So the density of air rho is 1.16 kg per meter cube. I have to find Fx, Fy, Fr and alpha. Here Q value is not given like the previous problem. So I am going to start with A1 V1 is equal to A2 V2 directly because I know the value of A1, A2 and V1. Knowing all the values, I can calculate V2 as 20 meters per second. From the given data, I have drawn the diagram in the similar fashion like in the previous problem. I'm going to apply Bernoulli's equation at section 1 and 2. Again, I'm assuming the pipe is horizontal. So the terms remaining are these. When I substitute all the values, the only unknown is P2, which can be calculated as 29.256 kilonewton. I have to solve for the forces on the bend in the x direction. I'm going to use the formula P1A1. P2A2, if you look carefully, it is towards the left. So I get minus P2A2 cos 45 minus Fx is equal to rho Q. The final velocity in the x direction is towards the right. So I take V2 cos 45 minus V1. When you substitute all the values, you will get Fx is equal to 19038.39 Newton. Now for solving along the y-axis, you will see P1A1 term becomes 0 because it has no component. P2A2 term in the y direction is downward. So I'll have minus P2A2 sine 45. If you see for the velocity, this term V2 sine 45 is in the upward direction. So it will be positive. If you look at the equation, you will get 0 minus P2A2 sine 45 minus Fy is equal to rho Q V2 sine 45 minus 0. I get the answer of Fy as minus 10507.6 Newton. Again, the negative sign will indicate that Fy is acting in the downward direction. The resultant force Fr is found as 2.946.6 Newton, and the direction of Fr with x-axis can be given by the formula alpha is equal to tan inverse of Fy upon Fx, whose answer I got as 28 degree 53 seconds. Let's take up another numerical. This question is for a vertical bend. Water at a pressure of 72 kilonewton per meter square. Water at a pressure of 72 kilonewton per meter square flows through a horizontal pipe of diameter 360 mm at the rate of 300 liters per second. So the pressure at section 1 is 72 kilonewton per meter square, which I have converted into Newton per meter square. Diameter of the section 1 is given as 360 mm, which is 0.36 meter. The value of Q is given as 300 liters per second, which is 0.3 meter cube per second. The direction of water is changed through 120 degree by a vertical bend. This term tells me that this question is a vertical bend whose exit diameter is 240 mm. So the angle of bend is given as 120 degree, which means we have to take 180 minus 120, which is 60 degree. And I have mentioned over here that it is a case of vertical bend. The diameter at the section 2, D2, is given to me as 240 mm, which is 0.24 meter. I can calculate A2 as 0.0452 meter square by using the formula pi by 4 D2 square. The volume of the bend is 0.14 meter cube. Since the pipe is vertical, you will have some water accumulated in the bend. So the volume of water in bend is given as 0.14 meter cube. We don't need the term volume. What we need is weight, because we are equating force. So another term which is equivalent to force is going to be weight over here. So I take weight of the water in the bend. W is equal to rho Vg. I am using 1000 for rho because it is water. Value of V is given to me as 0.14. I have substituted, and G is always 9.81. So the value of weight is 1373.4 Newton. The exit of the bend is 2.4 meter above the inlet, which means the height of the exit of the bend is Z2, 2.4 meter. So my Z1 can be considered as 0. Find the magnitude and direction of the resultant force on the bend due to water. I have to calculate Fx, Fy, Fr and alpha. Neglect friction and minor losses, which means I did not take into consideration any other losses. I'll first start by drawing the figure. I draw a horizontal axis and I draw the angle of 120 degree. Here the diameter is 360 mm, and here, at this section the diameter is 240 mm. The water is entering with velocity V1 and leaving with the velocity V2. At the section 1, the pressure force is P1A1. At the section 2, the pressure force is going to be P2A2. Since this angle is 120 degree and the total angle is always 180, so this angle becomes 60 degree. I am going to resolve V2 and P2 like I have done in the previous numericals. I am going to start with Q is equal to A1 V1 because I know the value of Q and A1. So I get the value of V1 as 2.947 meters per second. Q is also equal to A2 V2. So I get V2 as 6.637 meters per second. If I apply Bernoulli's equation between the section 1 and 2, I can calculate the value of P2. Now here what is important is Z1 is 0 and Z2 is 2.4. So I get P2 as 30.773 kilonewton per meter square. I would like to add a highlight in this part that Z2 is taken as 2.4 and not minus 2.4 because it is written here that the exit of the bend is 2.4 meter above the inlet. Had it been written that it is 2.4 meter below the inlet, then this term would have taken a sign negative and the other change would be in the diagram that this figure will be drawn downwards because Z2 will be then below and not above. The force in the x direction is given by this equation which is now well versed with you. So I get Fx is equal to 9903.79 Newton. For calculating the force in the y direction, this is the equation written. P1A1 term becomes 0. P2A2 term can be written. Fy term is same like the previous sum. The only term added in this question is the minus W, which is the weight of the water which is accumulated in the bend and it is acting in the downward direction. So I take it as minus W. Right hand side term remains the same like the previous problem. I get Fy as minus 4302.35 Newton. Negative sign again indicates that the force Fy is acting in the downward direction. Resultant force Fr is calculated as root of Fx square plus Fy square. That is 10.797 kilonewton. You can calculate the value of alpha using the formula tan inverse of Fy upon Fx. I get the answer as 23 degree 28 seconds. This is the diagram which I have shown. Fx is positive, Fy is negative. This is the value of Fr which is the resultant force and this is the angle with the x axis. So in this session we have seen the forces acting on a bend when the water is flowing through a pipe. Thank you.